Very good. So we start. So I will make a very short introduction. So Misha actually doesn't need introductions to complete this algorithm. So Misha received his PhD from the University of Oxford in 1994, and he went through several postdocs from UC, the study work with RHIC, yes, and also become a RHIC fellow. As far as the honors, the fellowship concerns, he received the Salome Research Fellow in 2002, and he is a ABS fellow since 2013. His research covered a very broad range. I'm not going to mention anyone except I just mentioned his most cited paper, co-authored with Rajagopal and RHIC, titled "The Signature of Tri-Critical Point in QCD." This is also, I guess, the subject of today's discussion. Today's title is Predicting Randomness, Relativistic Hydrodynamics. Yeah.
All right, that's very nice to be back. I'm happy that travel actually is working now. So that's so. I'm talking about randomness or emphasizing it in the title because typically we think of hydrodynamics as a deterministic theory of evolution of fluids. The physics that we want to address requires us to remember that in fact it is not a deterministic theory. And in fact, it describes a system which has intrinsic randomness in it and fluctuations, which of course inherent in any system with dissipation. So, and predicting how these fluctuations evolve turns out to be important for the physics of the critical point and other interesting questions in avionic collisions. So first, just a general introduction of framework. The best way probably to think about avionic collisions is compare it to the evolution of the universe after the Big Bang. There are similarities. In both cases, the system expands, cools, and freezes out. And what we see at the end are the particles which are free streaming. In the case of the universe, it's a cosmic microwave background radiation. And the thermal distribution tells us about these thermodynamic conditions at the time of freeze out. Similarly, the hadrons from heavy ion collisions, which are here. Basically, this is a snapshot of this final state seen by the star detector, carry information about the thermodynamic state. And we want to learn about the thermodynamics of QCD. QCD is a relativistic field theory, and thermodynamics of this theory is most naturally expressed in terms of the its phase diagram as a function of temperature and baryon chemical potential, which are basically the arguments of the partition function. In the and baryon chemical potential, as you all know, it just basically controls the baryon asymmetry of the system. The universe has a very small baryon asymmetry, negligible practically. Heavy ion collisions reproduce conditions. You can see these red dots is where the experiments determine that the freeze out has occurred. These conditions could be varied by changing the initial collision energy, indicated here. And you all know that this allows us to study the phase diagram or scan the phase diagram by varying the square root of S of the collision. This is the beam energy scan range. And the interest in this kind of physics is especially high because the way we understand the phase diagram, there is a critical point possible in the region which is covered or possibly covered by this guy. We want to find where it is. Of course, this is another difference from the Big Bang, where we have only one experiment and we cannot vary any parameters.
Excuse me, can I ask
Yes.
a question? I have to ask. And so when you do fluid dynamics, it's basically propagation of conserved quantities, density,
Yes.
where this energy that's conserved, and you can get equations of motion. So therefore, you need the equation of state as a function of those variables.
Yes.
So not the chemical potential,
Yes.
or the variance, not the temperature.
Yes.
So this means you need to somehow have an equation of state.
Yes.
It's not a triviality, but you will tell us how you do that, or you will just
Well, it depends. If you know the equation of state, then it's just what is it?
yeah, but it's not a
Use
triviality
thermodynamics.
because you know that, as you know very well, when you have a phase diagram like that, it's a multi-valued function, right?
Yes. Yeah.
So for a given mu, you have three different.
Yeah.
So it's
Yeah.
complicated. But,
Yeah,
but you have a procedure for doing that.
well, that is a standard textbook thermodynamics, right?
I'm not
So
so sure.
you can start with a so if we write equation of state in terms of pressure as a function of temperature, chemical potential, we know everything we need to know. If we we can find entropy.
No, because for a given chemical potential along this boundary, you have three different values.
Oh yeah, so these three different values is what we need to know, and we can find both
never
of
mind.
them.
That's okay.
It's just thermodynamics. There is nothing, and as you well know, temperature and chemical potential are the natural variables for pressure.
Not sure. Anyway.
Well, that's
Go
what I learned when I
go
was
on,
in
go
the
on.
undergraduate course of statistical, thermodynamics. So, and it's still useful. Now, the other difference, which is worth pointing out here, is again due to the fact that heavy ion collisions allow us to repeat the experiment many times and perform event by event analysis comparing the fluctuations between different observable events, which is also possible to do to study fluctuations in cosmology, but that requires you to look at different spots in the sky and then compare them, which causes certain limits on how, which is called cosmic variance. Anyway, so the important difference also in heavy ion collisions that this system is large enough to be treated thermodynamically, but it's not too large, not Avogadro number large, so that the fluctuations, which are typically suppressed by inverse square root of the number of particles, are not negligible. In fact, they are measurable. For example, if you look at the distribution of the number of events with different net proton number, you can see this nice, almost Gaussian curves, but these fluctuations are not exactly Gaussian. So not only, so typically in an infinitely large system, fluctuations are Gaussian. Again, non-Gaussianity is suppressed together with the magnitude. But in heavy ion collisions, even non-Gaussianity can be measurable. And that also could carry and does carry interesting information about the thermodynamic state of this system. In particular, if there is a critical point, this certain measures of the fluctuations should be non-monotonic functions of the collision energy. Now, what so far we have on that is the beam energy scan phase one, and the most interesting comparison could be made between the equilibrium prediction, and I emphasize that it's equilibrium prediction for the force cumulant of the fluctuations of baryon number, or the net proton number, which is what the experiments measure, as a function of square root of s. As you can see, as you go from one red point to the other, you follow this freeze-out curve, the green dashed line here, and the color indicates the sign of that cumulant of the fluctuations. You can see that it changes sign as you approach the critical point, becomes more and more negative, then switches sign, becomes positive, and then goes back. And that's seems to be what experiments are finding. This is a picture which is already now outdated. Let's see. Let me go back. Yeah. You can see that there is definitely a decrease followed by increase. Of course, there are still error bars, and that motivates this intriguing hint of this behavior similar to the one predicted for the critical point, motivates beam energy scan 2, which obviously would reduce the errors, which I indicated there. So most of you know what I'm talking about. And of course, an interesting question is whether this goes down. Has been already almost answered. It actually does. So this is more recent data. More recent analysis shows that notice that this direction of UB is reversed. It's opposite to square root of s. You can see that it actually appears to go down. There is more data which would fill this gap from fixed target, hopefully also followed by even more data from CBM at FAIR, possibly other experiments. So, and as theorists, we are very impatiently waiting for the results of beam energy scan 2, which is already on tape, and we want to see what.
Misha, a question there. So you have, for example, 7.7 center mass energy 9 there. So that means that in the quark ground phase, you just have very short time, if I understand.
Yeah.
Naively.
Naively, yeah.
So if you go lower energy, does that mean that even actually you don't have chance to go to quark ground plasma phase?
Yeah. Okay. I think this was basically the message which the conclusion of the SPS experiment wanted to give. That at some point you cross the threshold where the collision actually goes to begins in the quark plasma phase. But yes, at lower collision energies, we do not expect to even cross this bound.
Mm-hmm.
So, but as theorists, we do not just wait. We have our work to do, which is address the gap between the theory and the experiment. The theory, as I already mentioned, up to now, pretty much assumes the equilibrium in order to make some tangible predictions. However, we know that non-equilibrium physics is important in heavy collisions, and one can anticipate that it is even more important than the critical point because of the critical slowing down. So, because there are certain degrees of freedom, which collective degrees of freedom, which emerge near the critical point, which with the relaxation time becomes longer and longer and longer as you approach the critical point, and therefore they take longer and longer to equilibrate, and therefore as the system evolves, they stay further and further behind, away from equilibrium, and this at some point cannot be neglected. In fact, hydrodynamics itself simply breaks down if you are literally on top of the critical point for that reason, because you cannot talk about local equilibrium if the system takes infinite time to local equilibrium. That's critical slowing down. Of course, we don't get into this situation heavy ion collisions, but as we approach it, we have to take into account the fact that the system takes longer time to equilibrate. And so the challenge which it poses is to develop hydrodynamics with fluctuations, which are not always in equilibrium, but actually equilibrate as the system evolves. And that's what I'm going to talk about today. And of course, it is important, even away from the critical point, as I already mentioned, fluctuations are important when the system has a smaller number of degrees of freedom. So for smaller systems, like collisions of smaller ions, fluctuations become even more important. So if you want to go beyond hydrodynamics, this is the first step to add fluctuations. So now let me set up a framework within which we can understand the role and the place of fluctuations in hydrodynamics. So first of all, the way I think about hydrodynamics, we think about hydrodynamics, is that it's a theory which describes the evolution of the fluid towards equilibrium. But one should realize that this evolution doesn't describe it in all detail and on not all time scales, because there is a vast gap typically between the time that it takes for the system to equilibrate locally, establish thermal equilibrium. Like for example here, even though it looks very much out of equilibrium, but local equilibrium, we can be sure every cell in this fluid has a well-defined temperature. So one could really talk about the local equilibrium, but it takes much longer for this to settle to equilibrate all across. And the reason for that is that the quantities which takes longer to equilibrate are conserved quantities. They have to be transported or diffused across the system. And the bigger the system, the longer time it takes. It's not something which is determined by microscopic innate properties of the system, but rather by its size or how big those homogeneities in the system that it will start from are. And so the bigger they are, the bigger the separation of scales. And hydrodynamics describes only this process. And the reason that it involves only a few degrees of freedom is why this theory is so effective or so powerful or predictive. In the kind of modern language, we should think about it as a coarse grain or effective theory, where we basically lump all the microscopic details into certain spatially coarse-grained degrees of freedom, such as, for example, local density. One should remember in each hydrodynamic cell, there's just few numbers like density or energy characterizing each hydrodynamic cell, but because the cell has a finite size, these quantities do fluctuate. Although their fluctuations are suppressed by the size of this cell, when it's getting bigger, fluctuations are smaller, but they are there because we coarse-grain variables, microscopic variables, which are essentially, it's a quantum mechanical variable. They fluctuate. They become classical when you average them over large enough area, but they still have thermal fluctuations. These are the fluctuations we're talking about. And these are the fluctuations which are responsible for fluctuations of thermodynamics and hydrodynamics, and which are necessary in order to balance the dissipation. As I said, the separation of scales in heavy ion collisions is significant, but not infinitely large that you can completely neglect the fluctuations. There is about an order of magnitude of the separation. So one could have this kind of controllable situation where the first order approximations, you neglect the fluctuations, you can add them as additional ingredients. So now the way that one usually writes equations of hydrodynamics are basically writing conservation equations. So since we're dealing with relativistic hydrodynamics, this is how they usually look like. It's just conservation equations for four currents of energy, momentum, or charge. Or in general, much of what I discuss does not really depend on relativity. So in general, each of these equations could be thought of as a continuity or conservation equation for some density psi, be it energy or momentum or baryon number. And the conservation equation says that the local density could change, but only via flux of that quantity through the boundary of the cell, right, which is measured by the divergence of some flux vector. So I just write it this way generically. Now, one should realize that the way that this equation closes is that the flux in hydrodynamics, as everything else, is a function of these few variables which characterize the thermodynamic property of the cells. And therefore, we don't need to know any microscopic details of the state in which the cell is in order to determine what's the average flux. But it's true only for the average flux, right? If you have a thermodynamic ensemble, you're describing the thermal state of the system. In different members of the ensemble, the value of the flux will fluctuate, right? Fluctuate relative to that function which connects the average quantity to the average flux. These fluctuations, this deviation, is essentially due to local, much smaller than the size of the thermodynamic cell, fluctuations, and that's the noise which appears in the equation, making this equation essentially a stochastic equation for a stochastic variable. So I use red to indicate the stochastic quantities. This is the equations which basically define the stochastic hydrodynamics, or hydrodynamics which involves fluctuations in the Landau-Lifshitz approach. Now, so therefore, so I want to say that solving stochastic equations is not the only way to deal with the directive, right? So one in principle could just set up this, do a random number generator and solve the stochastic equations. There are certain problems with this approach, and that's why another approach appears to be actually promising, and I would say is better, because it solves deterministic equations for quantities which characterize the fluctuations. So the mean, the average of the square of the correlation function, if this is just variables, they don't have random numbers or random fields. So their fluctuations characterized by this kind of correlator. And of course, one can continue. There's a 3-point function, a 4-point function. I will just focus for this kind of schematic representation. So while the stochastic equations, you solve this stochastic equations, here you have deterministic equations, which describe essentially the same evolution, but in terms of quantities which evolve deterministically, right? So you can see that in this case, flux again depends on the mean value of our variable psi, but it also depends on the magnitude of the fluctuations and on the higher orders like skewness, kurtosis, etc. If you want to extend this, of course, that has a disadvantage that you have to have additional equations for each of these quantities, but these equations could be also obtained, and they are also deterministic. Each of these quantities are not conserved; they simply relax to what they should be in equilibrium. In equilibrium, all the fluctuations are determined by equation of state, essentially. This is basically a relaxation to equilibrium with a rate which is twice the rate of the evolution of, for example, if this is a fluctuation of some diffusive quantity which diffuses, its 2-point function, which is a square of the walls twice, with twice the rate. So, and one of the drawbacks of this approach is that, remember, this noise has to be microscopically local, and in practice, that means that it introduces ultraviolet divergences. So, in other words, there is a dependence of the dependence of your results on how big you make this hydrodynamic cell size. Of course, it's unphysical, but it is there if you do this calculation, and it can be eliminated analytically without having to do this cancel. There are of course cancellations which eliminate this, but rather do it numerically, you can do it analytically and arrive at equations which are in a way renormalized, that they deal with quantities which do not depend on the count. This is kind of the main advantage of this approach.
So Misha,
yes.
Outside question. So nobody doing left-hand one.
People are doing that too.
In practice.
Yeah, in practice.
Oh, really? So
yeah, but
so
not,
the code.
well,
I know.
not for real, in some
The
model
right one.
calculation.
I know all the familiar names, but left one.
Well,
Anybody
there's
doing
Kapusta, Gale.
Oh no, I thought they have a book on this. I thought they have textbook on this, but they also put on the code, for example. Oh.
You mean this or this? The left-hand side? No, well, now Lifshitz were not thinking about the code.
I know.
They just wrote equations.
Oh, how about the Gale Charles?
Well, yeah, they have code.
They have
And
code.
then-
You using
yeah.
this?
Yeah, yes, and they're dealing with this issue that you know this noise must have a correlation function. It's a delta function. Now, if you want to have a delta function of widths, you have to regularize it, right? So the widths have to be small, so the height has to be large. So the magnitude of the noise tends to infinity.
That's true.
So that's called sometimes infinite noise. So what happens is that you have an infinite noise which drives a finite evolution. The reason that you get finite evolution is because this noise is correlated, and so it averages away.
Okay.
So it's local, even though it's infinitely large, it's also infinitely, it's correlated on arbitrarily small, right? Numerically, it's a nightmare, right?
But people are doing that.
People are doing it by doing some kind of smoothing, etc. So I'm not saying that it's undoable, but you have to deal with this
There are also
separately.
people doing Langevin, just Langevin equations for the noise, right?
Of course, yeah, and that's what you would find. So one thing is just to just simulate Langevin equation for 1 degree of freedom. That's fine. You have infinitely, if the degrees of freedom are fields, you have to deal with essentially infrared divergence, right? So as usual, like in the quantum field theory, right? Your finite values of physical quantities is a cancellation between infrared divergent one loop contribution and ultraviolet divergent radiative corrections and the counter term, which is also infinite, right? So something like this happens, and you don't want to do it numerically, right? Because basically your precision is lost in this infinite cancellation. Your result is infinity minus infinity. That's what you have to deal with. Of course, in practice, one can kind of deal with, but if you want to be numerically kind of precise, and you really want, that creates some problem. Because this dependence is unphysical. And this deterministic approach doesn't have this problem. One can basically analytically subtract those divergences before you do the simulation. So you deal with a finite system, a finite sense of there are no ultraviolet.
So now you understand also the right side one is kind of doing truncations, right? Basically, you can improve by including more terms.
Yes, but that truncation is controllable. In the same way as hydrodynamic itself is a truncation.
Mm-hmm.
When you say that this flux is a function of this variable, it's a truncation. It's a function not only of variable, but also gradients of this variable. And second gradients. The third, and you throw away the higher for the gradients, right? That's the same truncation that throws away, let's say, turns out the same parameter controls. For example, I here truncated it to quadratic fluctuations. Cubic fluctuations will be smaller by a kind of controlled by the same parameters as this gradient expansion. So, so one example of this theory, which is kind of simple, but it's most relevant to only involve one field, most relevant to the critical point, is a theory which we call hydro and it's basically based on observation that near the critical point, we already said there are some degrees of freedom whose equilibration time becomes arbitrarily large, like psi, which is the correlation and convergence of the critical point. And therefore, since hydrodynamics breaks down when there's not enough time to locally equilibrate, as this equilibration time becomes large, hydrodynamics breaks down at already for quite slow processes, right? And that so you cannot study processes which are fast enough or fast compared to microscopic scale. However, one can extend the range of applicability of hydrodynamics to show the times by adding additional degrees of freedom. This is quite a common situation. So turns out that these slow degrees of freedom are fluctuations. And again, the first two in the systematical kind of correction to hydrodynamics should be 2-point fluctuations of the slowest hydrodynamic variable, which is specific entropy overlap. It is slow because, unlike, let's say, pressure or density itself, it's not susceptible to, let's say, sound fluctuation. Compressions, we do not change it because it's a ratio of two densities. So it only can evolve diffusively. That's why it's the slowest model. Moreover, near the critical point, the diffusion constant of that mode also vanishes. So it's really the slowest mode. So one can imagine a controlled limit in which you are close to the critical point. So this mode is slow, the slowest and the last one to equilibrate. And the way to describe it, this 2-point function, is to, in terms of this kind of Fourier transform, which is basically Wigner transform with respect to the distance between the separation between these 2 points. The reason that it's convenient is because that scale over which this length scale over which this correlation function varies, this correlation function, when you change the separation, is much shorter. So it's convenient to do this kind of transform and consider this as a kind of a label, this corresponding wave vector Q, which basically tells us the wave number of the kind of fluctuations at different points x, which is basically the midpoint. So the variation with respect to the midpoint of this correlation function is according to longer length scales. So what does this want to do? Well, it wants to be in equilibrium, which is given by thermodynamics, which we know. It's basically some Cp, the heat capacity at constant pressure, multiplied by some function of Q, which we know from, supposed to know from thermodynamics. And in order to understand how to relax it, it's better to think in terms of one Sager picture of this relaxation processes. Equilibrium basically maximizes the entropy. The entropy usually is considered as a function of dynamic variables, like just energy density and charge density locally. But now, if the system is out of equilibrium because the fluctuations are not in equilibrium, there's additional contribution, rather a lack of entropy. So since you know something about this fluctuation, you know more. And remember, entropy is by definition is a lack of information, right? So the most likely state is the one which you have if you don't have any information, is maximum entropy. This one is not the most likely because you know something about it. And there is additional relative entropy relative to the maximum entropy, which is thermodynamic entropy. You can calculate this, and it has this form, which is recognizable in quantum field theory in a different context. So the main property of this is that it's always negative and achieves the maximum equal to 0 when phi q is equal to its equilibrium value. And so remember on Saga picture, the rate of the evolution, sorry, the time derivative of quantity is basically equal to on-Saga coefficient times the force, which is derivative of entropy with respect to corresponding variable. And the corresponding rate is easy to anticipate. It's just twice the diffusion rate of this specific entropy, right? And as already said, this diffusion rate vanishes as correlation length psi diverges, and the typical wavelength, which is a correlation length, being giving you the typical rate, which is basically psi to the power minus 3. So it also vanishes. That's how slow this becomes. And if you also remember your textbook hydrodynamics, the bulk viscosity in this situation is dominated by the slowest relaxing mode and is proportional to the time, this relaxation time. So the bulk viscosity diverges. That's one way to see that hydrodynamics have to break it down, because hydrodynamics is expansion in gradients and bulk viscosity is coefficient in this expansion. The Taylor coefficients become large, Taylor expansion doesn't work, and that happens to the critical slowing down. So another interesting consequence also discussed in the literature of this of the fluctuations is that if you look at a very low frequency response of the system in the same bulk channel, let's say to compression, can characterize it by frequency dependent bulk viscosity, well, it will be non-analytic. By low, I mean even slower than even though the system has enough time to relax, there is still some what is called long time tails in the response, which are due to non-analyticity. It's another consequence of this, which could be derived in this theory. So this theory has been implemented in a kind of toy model simulation by a couple of groups, and basically one could learn some lessons. So if one look at this quantity which describes the fluctuations, remember you can think of this phi q as a function of q is amplitude of fluctuations at a given wave number, wave length. So you can see that it's there is some characteristic one. So let me put it this way. So the dashed lines are essentially the equilibrium. This is to which this correlation function, if you wish, or for smaller q, the phi q is bigger, and that's why it wants to relax. But if the initial profile at tau equals 1 Fermi was like this, and may have been in equilibrium, and you approach a critical point, and the equilibrium becomes larger, fluctuations increase, right? Well, the non-equilibrium one, the ones which follow the evolution equations, do not quite follow. You can see they follow at large q because remember the relaxation rate is the diffusion rate proportional to q squared. So at large q, relaxation rate is large enough that you keep an equilibrium, but at small q, you don't. So that creates this characteristic peak, and you can see that q equals 0, where relaxation rate vanishes because of the conservation. The integral of the whole volume of this quantity simply cannot change. So we see this. We see the memory, as you can see, that the system evolves, and in the, when you pass the critical point and the equilibrium fluctuations go in the reverse and become smaller, well, then the non-equilibrium fluctuations have to also do the catch-up game. So there is a lag. Another interesting consequence you could see if you look at the evolution in space, so this is the radial expansion, essentially drives the maximum of the fluctuation where the critical where the system is, it's inhomogeneous, it's closest to the critical point, it basically drives this function, so advects it with the flow, phi q. And another useful consequence, especially for simulation, is that feedback, at least for the parameters which people are using here, is actually quite small. So one could actually quite faithfully study the behavior of the fluctuations on top of just the normal hydrodynamics. So it simplifies a lot the calculations. So this only considered, this Hydro+ approach only considered one mode, the slowest one, which is entropy per baryon, or specific entropy, which I call M here. Obviously, especially for more general applications, or if we want to see how we approach what happens when we approach the critical point, we want the theory which describes fluctuations of all dynamic degrees of freedom. And well, if you count baryon number, energy density, and momentum density, there are 5. If you diagonalize hydrodynamic equations, the eigenmodes are specific entropy, pressure, and velocity. So there are 5 variables. I will just collectively denote it by phi. And the way one could write these equations directly, rather than appealing to the arguments which I gave before, is taking this stochastic equation, which contains this stochastic term, flux, on the right-hand side, and expand it in fluctuations. Right? You get the linear term, which vanishes by definition of the fluctuation. You get quadratic term, which when you average, it gets you the 2-point correlation function. So here you are, you have time derivative of your average variable on the left-hand side, and you have some function of the 2-point function on the right-hand side. This procedure could be done. There are interesting questions which arise. If you want to do it in a relativistic context, you want to when you do the averaging, you need to do it at the same time, so the equal time averaging. But what does equal time mean? It's not absolute concept in relativity, right? So how do you define equal time? That's one question. I will say one transparency on that. And also, what do you do with ultraviolet divergences, which inevitably appear when you have a fluctuating variable, as I already described at one point? This is the problem that people have to deal with numerically, and that is where the realization comes in. So first of all, the equal time. Well, the natural choice, well, to answer this question, you need to ask in which frame. Right? If you define a frame, then in this frame, so obvious choice is the rest frame of the fluid. Right? It cannot be the lab frame, because this has to be more attuned to the fluid itself, should not, right? So, okay, but the velocity of the fluid, this is a 4-dimensional vector, so they point in different direction means different velocity, right? Different. So when we, for example, want to write, for example, evolution equation for this correlator, we want to know how this correlator at the same separation differs in 2 points. So we take spatial or time derivative of this correlator. So we want to take derivative of this correlator at fixed separation at different midpoints, x. So I just write it in this way. So if you do it just like this, you can see from this picture, then the same separation vector is no longer equal time. It's no longer orthogonal to the flow velocity of the fluid. So you cannot just fix y. The solution is simple. You just take this y and you boost it by the same boost lambda, which you need in order, well, to get from the velocity of fluid in point x to the velocity at point x plus delta x. Then you can see that the new boosted vector is also orthogonal to u, so it's still equal time. So you measure the difference between the 2 equal time correlates. When you take, the calculus limit, delta x to 0, that defines your derivative, which is kind of, which is not this. There is no name for it. We had to come up. It's similar to covariant derivative, but it's not. We call it confluent derivative because it's related to the flow. Right? So that's one of the objects which we have to introduce in order to describe the dynamics of fluctuations in the relativistic hydrodynamics setup. Then the question of ultraviolet divergences, as I already said, this 2-point, well, the square of the field in the same point, averaged, is infinite. And you can see this in two ways. Well, the simplest way to see it is to remember that in hydrodynamics, in equilibrium at least, all correlation functions are essentially delta function, right? Delta function at zero separation is infinite. Or Fourier transform of delta function is a constant. So if W, which is the Wigner transform, right, the Fourier transform with respect to the separation, is a constant, this integral is ultraviolet divergent. This is a typical situation in quantum field theory. It's the fact that you have products of fields in the same point that causes ultraviolet divergence. It's very similar. And the solution is also very similar. So the terms which contain this correlate, I just denoted them by this kind of symbol. They're not just equal to this. It's just some function of this term. Does not matter what it is. What is important is it contains some ultraviolet divergences, but what is also important that they are all local in terms of the average fields. And therefore, their form is the same as the form of these terms, such as this is the energy, this is the pressure, and this is the viscous tensor, which basically contains local gradients, which are local. So there's some linear combination of these terms here, which is divergent. If you absorb them into the terms of this, which I have written explicitly, it renormalizes hydrodynamic variables, energy, velocity, density, as well as pressure. And what is left there is finite. So one could say that, like in quantum field theory, you have, if you started with this equation of state and these variables, you will be simulating the system with different equation of state. This is like a bare equation of state, right? So if you want, and it will depend on what cutoff you have chosen. So what you want to do instead is start with some equation of state which is different from what you want, different by the amount of these infinite terms, which you will then absorb. But the end result, this is a kind of philosophy of this, but the practical application is that you can start with an equation of state which you know is physical, and use this renormalized corrections, which are finite. And they describe all these effects which I already talked about, such as, for example, long-time tails, these non-analyticities which arise, are all there, and they are all physical and cutoff independent. So another interesting observation one could also make is I already mentioned the Wigner transform of the correlation function, one correlation function. Again, it's sort of similar to the particle distribution function in phase space distribution function in kinetics theory. It's also, in fact, is a Wigner transform, but mathematically, not physically. It's a completely different story. However, there's more similarity, because if you take longitudinal components, that is the fluctuation corresponding to pressure and velocity fluctuations at fixed specific entropy, which is essentially sound fluctuations, and ask what equations does this Wigner transform obeys this Wigner function W longitudinal. It obeys identically is the same equation as you could derive by just starting asking questions, what should be the equations for relativistic kinetic equations for phonons, and so on, right? And we're talking about the sound, so it's quite natural. So these are basically particles whose dispersion relation is linear with the velocity which depends on the position in space. Different points in space could have different velocity. And as a result, and it relaxes to equilibrium, given by the Bose Einstein distribution. This is what the meaning of this function is pretty clear in this context. What is interesting is that if the, so think of this, the phonon in each, physically see what is it to understand, is that in each cell, phonon, or in each kind of subvolume, the phonon moves basically with velocity, speed of sound along a straight line, right? But this velocity is different for one thing and in different positions in space. There's also the fluid accelerates itself, it rotates, right? So if you look at the trajectory of the phonon, you can interpret it as inertial forces acting on it. And this all comes out in an equation. You find the forces due to acceleration, rotation of the fluid, and also what we call Hubble forces when the fluid expands, like redshift. When the fluid expands, the phonons stretch, the wavelengths become smaller. All this comes out from a calculation which didn't mean to even talk about phonons. We're talking about fluctuations. So it gives us confidence that these are the right equations because they describe the right physics. So finally, well, not, yeah, I think it will be finally, right? How much time?
15 minutes.
15 minutes, yeah. So let me talk about non-Gaussian fluctuations since they're important for experiments. What we do in this case?
You can talk as long as you like.
I would like to conclude on time if I can, and then we could have discussion as long as you want. So I have only two topics to cover: the non-Gaussian fluctuations and a little bit about freeze-up. So non-Gaussian fluctuations. The main philosophy I already have covered. We basically now talk about the equation, deterministic equation, which describes not only evolution of the mean, which is now a function of the flux is now a function of the cumulants of the fluctuations, third, fourth, etc. And the second we already discussed. And each of these cumulant will have equation for itself, which has a similar structure, except that this will not be a conservation equation, it's just relaxation to equilibrium. Now, of course, this is undoable, solving this problem, because each equation contains infinitely many known functions, and there are infinitely many equations, right? So in principle, it's well posed, but it's practically unsolvable. However, we should remember that we are in a controlled situation where fluctuations are small, because we are it's the same conditions which are required for hydrodynamics operational scale. Suppress the magnitude of fluctuation and make them also more Gaussian. And in practice, that means that the cumulants actually have a hierarchy. There is basically a small parameter which controls the magnitude of the cumulant. And if you write those equations and truncate them to lowest order, then a very simple structure arises. If you just stay at lowest order, they are completely recursive. Each subsequent equations contain only the lower order cumulants. So, and it's even linear. So each cumulant, for example, this one, relaxes to its equilibrium value, right? Which depends on, or the mean value, relaxes to some function of this. It's not written quite correctly, but I just wanted to give you the flavor rather than to write exact equation, which is a function which to some value which depends on the values of not necessarily equilibrium values of low order correlates. So you solve the first equation, then the second equation is linear. You solve the second equation, then the third equation is also linear, etc. So it makes it very easy. If you want some feedback fluctuations like long time tails we discussed, you need to go to next order. In a sense, this organizes itself as a kind of loop expansion. And in particular, rather than writing equations, one could understand their structure by just drawing some diagrams, which I just indicated here. You can see time derivative of a 3-point function contains two terms, each of them vanishes has such a form that it vanishes in equilibrium. Just if you focus on this term, this is the rate of the evolution, and this is the difference between two diagrams which cancel on equilibrium, essentially, if you think about it. Which is what you would expect in like Onsager evolution. Each of these correlation functions relaxes to equilibrium. As I said, to leading order, these diagrams drawn in this way are tree level. If you want to expand to high order in this smallness parameter, you naturally get loops, etc. So another object which we also need to introduce in order to study high order point, we also need to generalize the Wigner function in this case, and there is a natural generalization which we came up with. Couldn't find it in the literature either. Apparently nobody was thinking about this before, but we needed that. So, so you can see it's basically like a Fourier transform where we fix the midpoint. So there are n integrals with one constraint. So for example, for 2-point functions, you get that you just one integral, right? But you can write it as two integrals with respect to x1 and x2 with a constraint that x1 plus x2 is fixed. And that's what it does. We normalize it in such a way that when n equals 2, you get the same definition as so this kind of Wigner transforms actually a natural object to describe the evolution. And so they basically tell us about somehow interactions of these fluctuations of different wave numbers. All right, so we could even try to run a very simple simulation. We did this just to see what happens with this fluctuation accumulants when you expand past the critical point through a crossover region. So this is one way to look at the critical point, temperature versus density, which is what likes, right? I understand. So we could do that too. So you expand past this point, you can see that as you approach the critical point, this is equilibrium fluctuations increase and then decrease. The skewness goes negative then positive because it's on different sides. Kurtosis does this, etc. But the actual fluctuations are falling behind, and the smaller q is the further. So red one is the smaller q, blue is the larger. You can see the blue one is almost able to catch up, but the red one is not. And it's important because what we see are not those fluctuations. We cannot control the scale at which these fluctuations we measure because of the thermal, if you wish, broadening. We measure momentum of the particles, not the position from the fireball that they originate. So there is kind of broadening. It effectively means that we will be looking at some kind of information about hydrodynamic fluctuations in terms of these variables for small q. And that will naturally suppress the fluctuations, which of course is what we should expect because of the conservation laws. Conservation laws should suppress the changing of the fluctuations. Right? If it was strictly enforced, there would be no evolution at all. Finally, as I already said, we need to translate fluctuations into hydrodynamics, which we cannot measure. There's a correlations of densities at different points. What we could do is correlation of momentum of the particles. And in order to implement this, so in this paper, there is my student Krishna and his students. So we ran this kind of sort of simplified model just to see how the fluctuations in hydro plus. The model is just one single node, translate into fluctuations and correlations of particles. The simple model we use is basically we think of the matching the hydrodynamics on one side and some kinetic theory with on the other side, but we need some correlations between the particles. In order to introduce them, we add this kind of background field which fluctuates, and its fluctuations induces and it couples to the particles, and it therefore, for example, it could change the mass of the particle. That changes the distribution function, the equilibrium, and so the correlation of this critical field, which we call sigma, is translated into correlation of a particle distribution function and ultimately particle multiplicities when you integrate over phase space over acceptance. This integrals over acceptance. And so what we have to do is to basically relate this kind of field, intermediate field that we introduced, to actual hydrodynamic variable. Natural choice is just to say that this is the two-point correlation with some kind of normalization. That's what we do. And now we want to see how this translates into some potentially measurable properties. One thing is we could see that conservation laws naturally cause anti-correlations, which basically compensate the partial correlations at shorter rapidity separations. So if you approach the critical point, there's a peak which is rising, but it's accompanied by a dip at larger rapidities because or rapidity separation because of the conservation effect. You can see that the typical width of the peak is just basically controlled by the thermal rapidity. Which is, for the one. The other interesting consequence is you could also see that although in equilibrium, the magnitude fluctuation depends significantly on how far the system travels past the point of maximum correlation lengths below the critical point. So the lower the freeze-out temperature, the smaller the equilibrium. So these are the two examples. At 156, equilibrium correlations will be larger than at 140 MeV. And this is just a function of the maximum correlation length. So for different trajectories going a different distance to the critical point. This is true for equilibrium, but for non-equilibrium, the difference is much smaller. Precisely for that reason, even though equilibrium fluctuations are larger, but the system takes longer time to get there. So there's a competition. So at the end, the result depends. First of all, it's smaller. You can see here the maximum is, it reaches up to 8, but here we have only 2 or so in this kind of normalized units. But the dependence on the freeze-out temperature is not so significant. That's an interesting consequence of the conservation laws. So this is my last transparency. So we are basically working on developing the hydrodynamics of with non-Gaussian fluctuations, which involves all modes, not just density, as an example I showed you, but also pressure and flow. This is an interesting problem. Again, in my last transparency, I discussed how to freeze out Gaussian fluctuations, right? So we haven't yet done, but we need also to learn how to freeze out non-Gaussian fluctuations. It's another interesting problem. The problem, which is longer range probably, but more interesting, is what happens with respect to the phase transition, and whether our understanding of fluctuating hydrodynamics may help us to understand this better. It's a very challenging problem. And of course, we need to learn how to put it in the realistic simulation and compare to experiment. Thank you.
Thank you, Misha. So, any questions?
I just have a comment. I think to me it's very important that you have gotten this feature in that the time scale for the different fluctuations near the critical zone are different. So what you finally see is a sort of totally distorted image of how the conditions are at the critical point. And that seems to be very essential. So
I would not say totally distorted, but
somewhat distorted, let's
distorted,
say.
and we need to understand how.
Well, how much and so on depends, I guess, on the specifics. Yeah. But this is very nice to have this included. Very important.
So is that distorted meaning the shift?
Was that what he explained that some of, well, you could show the figure. What,
You're referring to this picture. Right? This one or this one?
no, why would you say, next one,
Yeah,
this one there,
this is
top
the
right,
left.
top right.
Yeah, this
That's
is a
right.
function of sort of time.
Yeah, yeah.
Of course, you make a measurement only at one point, right?
Yeah.
So if you freeze out, let's say somewhere here, past not too far past the critical point, which we hope is the case, you can see that obviously, if you are closer to the critical point, the magnitude will be bigger, but it will be smaller than the magnitude at the critical point. So if you just if your characteristic wave number of fluctuations which matters for this freeze out is small, it could be significantly small. So, but there is still this non-monotonic dependence of these measures on square root of s will still be there. But in order to correctly, reliably calculate the absolute magnitude of this effect, you need to take into account the harmonic linear. So, most of the estimates that we have do not take this into account, but I kind of was always trying to be careful not to claim that I know what the magnitude of the effect is, because it depends on many factors, and this non-equilibrium physics is important.
I have a question on this, the last volume. What do you mean a scale of the fluctuation?
That's what I mean by scale. I mean the spatial scale. So the Q essentially is a wavelength of the fluctuation. So if you wish, the value of this function W at Q basically tells you how big are the correlations at this spatial scale.
1 over Q.
Separation, 1 over Q. Yeah, so 1 over Q small means a large scale. Now, when you freeze out, if you were able to, let's say, do the measurement at 2 points which are separated very close to each other, let's say, 1 Fermi or so, right? Then you would measure essentially fluctuations at Q, which is, let's say, for the 1, which evolve fast enough that they are basically close to equilibrium. But when you do the freeze out, you cannot do this. The particles which end up with the same momentum actually came from a different cells, right? Because there is the momentum of the particle. Let's just think of longitudinal momentum, rapidity, right? The rapidity of the particle is the sum of the rapidity of the cell from which it came and its rapidity with respect to the rest frame of that cell, right? And there is basically particles could come with cells separated by rapidity half or even 1 if they are ions. They could come from different cells, so they are separated by. So when you measure the correlations between the two, let's say, kinematic rapidities of the particles, you do not measure the correlations between the two volumes separated by this distance. You are smearing the range of spatial rapidities which you are correlating. That effectively means that your resolution scale, in terms of what correlations you actually, what spatial scales of fluctuation, what wavelengths of fluctuations are being measured, is set up by that smearing, thermal broadening, right? So that corresponds to smaller Q, right? And that means that the signal will be small, and it has to do with combination of two effects. One is the thermal broadening, And two is, well, the conservation. Conservation slows down evolution of this kind of long wavelength. Think about it this way: if you measure the in the extreme case, if you measure the fluctuation of the total baryon number, it's zero because it doesn't change, right? So, but you cannot measure the even with the smallest kind of rapidity bin. You would still find contribution of particles from a range of spatial rapidities in the fireball. And that range multiplied by working time gives you the distance between the, that you can throw, right? And correspondingly, one of these distances that, when I talk about the scale, I mean that spatial scale.
So it's convoluted with the
yes.
thermal. Is there optimal,
Yes.
optimal Q scale? Could there be in principle? If we know few parameters. Like
well, we could estimate. So let's say we have pines, right? Pines at the temperature of result of water, their mass, roughly speaking, has a typical average thermal rapidity of 1, right? It means that the resolution scale of your kind of spatial measurement of this, you are kind of coarse graining your correlator, hydrodynamic correlator, which really gives you at arbitrary scale, but you are coarse graining it when you do this. How to say? So when you particularize it or freeze it out, right? So that scale will be basically 1, which is rapidity, times tau. Like the spatial distance, roughly speaking, is tau, which is the freeze out time, working time, times 1. Right? This is C, working C, right? So you take 1, you multiply it by what? 10. So you get 10 Fermi, right? That is the scale at which you are measuring. It's probably too large because the scale probably has dynamics already. But anyway, let's say maybe if you think for pines, the range is not 1/2, and tau is not 10 but 7 or something like this. So you get something in the range of 5 to 10 Fermi, let's say. This is the, so you invert it, that is the Q that we are talking about, right? And this is, at this scale, fluctuations take longer time to equilibrate than at a microscopic scale for the 1 Fermi, right?
Thank you. Any other question?
Yeah. So what exactly is Cooper-Frye mechanism?
Cooper-Frye, did I mention? Yeah, I mentioned it. So, next. Yeah, so Cooper-Frye, I think it's, did I mention it? Oh yeah, Cooper-Frye, yes. Cooper-Frye is a standard theoretical tool to convert hydrodynamics into particle observables, right? Such as the inclusive particle spectrum, right? And the idea is very simple. So hydrodynamics gives you temperature, right, and chemical potential, right? Then the distribution of particles which experiments observe at freeze out are given by equilibrium distribution at that temperature and chemical potential for each particle. That's what Cooper-Frye does.
In hydro, there's no particles.
In hydro, there's not, but there is temperature and chemical potential.
Stress momentum tensor to convert that into particles.
Yeah.
But it's not, it's in question. Cooper-Frye.
Yeah, but this only works, the original Cooper-Frye only works for single particle mean phase space densities of particles. not for fluctuations.
You have correlations.
Right, so if you want to describe fluctuations, you need something more. You need to say, okay, so what, how do you match the hydrodynamic flux? So hydrodynamic mean values could be matched, as we said. Hydrodynamics gives you stress tensor and currents. From that, you can extract temperature and chemical potential. From that, and flow velocity. From that, we can calculate what is the distribution function for each particle, right? And it's extremely successful. So it works all the time. So what we're trying to do is to generalize it to the following. Now, hydrodynamics gives us not only the mean values of energy density and variables, but also their fluctuations. So how do we match or translate those fluctuations into the delta F, F being the distribution in phase space, which can then be used to calculate experimental observations.
Sure. Just a question. So one thing that's happening is the system is getting bigger, right? As the collision evolves.
Yeah.
So at some point, the hydrodynamic assumptions must break down.
Yes.
So are you confident that these freeze outs and things like that happen? The hydrodynamics is still good when these freeze outs?
So, well, the freeze out. So the moment you describe is precisely the moment when freeze out happens.
Not necessarily. I think you could have some variables that should maybe freeze out earlier. Something
That
like
could
a
be,
color
yes.
or something.
That could be, yeah, that could be like a cosmology. Yeah. Yes, of course, photons never even thermalize. They just emitted from the thermal plasma. They don't even participate in it. So yeah, they are emitted at
But it's also definition of freeze out, because they don't interact. They freeze out.
Yeah, so they freeze out immediately. They're never even part of the hydrodynamics. And yes, there are some particles which seem to have slightly higher temperature than this kind of freeze out. So within this kind of discrepancies, the picture of the freeze out works. And if you want to account for them, one could make special consideration for those, for example, hadrons whose cross section is smaller than typical, and therefore they freeze out earlier. And one could actually see an experiment that the typical characteristic, the slope of the Boltzmann distribution is different and corresponds to
I will stop recording.